Hello, everyone. My name is Hamid, and I'm associate professor at the University of Southern Denmark. Today, I'm going to talk about some of our results that we obtained on fault detection and diagnosis. Well, yes, this is a paper that we basically reported in this EnergyInformatics. So the work is done actually in collaboration with Attila Santos and Bo. Uh, and is actually this report some of my results of my research activity related to smart buildings. So I'm also running other projects within area of smart energy networks. So to be more specific, actually, I'm presenting some of my results related to Celsius project. And this is a project which is actually focused on IoT solution on a smart buildings, and it is financed by EUDP under basically and the Danish Energy Agency. Well, to set the scene actually for the work that I'm going to present, I would like to show you some statistics. So if faults in buildings actually is responsible for financial loss and also for energy inefficiency. So there is a study in 2005 which actually shows how much different faults affect annual energy consumption and also annual energy of annual cost, financial cost. So this you can see here. Yes, it's a bit old. We have also basically more recent result again in the US that we see that actually fault is responsible for financial costs and also for energy inefficiency. To come closer to our own place, so our experience also confirms that actually fault affects basically energy efficiency and also causes financial loss. So we have an experience in one of our buildings, OU44, which actually I'm going to present my result on OU44 today. So we had a fault in CO2 sensor, which causes actually our ventilation actually to run unnecessarily. And some simple calculations showed that actually you could avoid 414 US dollar per week if you could detect this fault earlier. So this is just to give you an idea how important it is to basically detect fault as early as possible. So consequence of fault is on energy consumption, is on financial, it's on economy, finances of buildings, and also in on comfort and health. So that's why actually over the years we have focused some of our research activity within this area. So, okay, let's talk about the paper and the result that we are reporting in a paper. In the, what we are reporting here is basically to come up with a kind of condition indicator for buildings. You remember at the start of this pandemic, actually, we had the people, with thermometers at the airport, different places, and checking for the basically symptoms. If they were checking if someone basically has a fever or not. Why? Because fever was actually kind of condition indicator, health indicator that could say if someone could be possibly basically infected or not. So we are looking for the same thing for buildings. So we get data from sensors, we do some calculations and some computations, and then we come up with a number. And this number, like the degree of a fever, basically can tell if the building is healthy or not. So that's the overall goal. So to be more specific, what we do is that actually we present actually a data-driven method that gets data from sensors. So it's not model-based. So we only work with data from sensors. What we do is that we use multivariable statistics, more specifically t-squared statistics, to basically do our calculation, to quantify, to get all the data from the sensors, and then quantify, and calculate one measure, so which actually encodes all the information about the health of the room in particular. So the good thing with the result that I'm going to present with more detail just now is that it is scalable and it is adjustable. So if, for example, you have a building or you have a room that doesn't have a CO2 sensor, but it has some other sensor, so it doesn't matter that much. I mean, it can be adapted to that. And also implementation-wise, it is simple. So yes, a bit of mathematics. And I know it's close to launch in Denmark, and also, you have already seen a lot of presentations, so you don't want to see too much mathematics, but just I want to give you an idea of this one. The mathematics behind the method is that what we do is that we have all the data from the sensors we get within one room. So what we do is that we do basically some sort of dimension reduction. So we basically catch the most important properties of the data, the most important information of the data, and throw it out. And by data, I mean training data. For example, let's say you have data of 100 days related to the room sensor data. So you just want to use this 100 days as a training set. So what you do is that you want to capture the most important behaviors of your sensors within a room. So what you do is that you reduce the dimension by avoiding, actually, by throwing out unnecessary information of the sensor data, and then coming up with a projection that actually contains all the information. Then, and this projection here is P matrix in this, and here, I mean, this psi actually is your reading of a sensor. Then, of course, you use this one. This is the only tuning parameter that you have for your condition indicator. Then you basically use this condition indicator on real time. So it gets information from the sensor, use the same projection, and check if actually this is within a threshold or not. The threshold actually is calculated from the equation at the bottom. So it depends on the dimension of the data, dimension that you reduce, and also F distribution. To give you an idea, I mean, how we come up with this threshold is based on hypothesis testing. So the basically probability of the data to be outside this threshold for a normal situation is very low, very low. So that's why, I mean, this basically gives us a rule to check actually if it is if the room is healthy or not. So that's the mathematics behind it. Of course, you can read more in a paper. So it's more dimension reduction, and also a bit of multivariable statistic and hypothesis testing. Of course, multivariable one. That's why you use F distribution. Well, let's have a look at tests, because I know that this is more important for you than mathematics behind it, because implementation-wise it's easy, so you don't need to know all the mathematics behind it to be able to implement it. Yeah, and I think algorithm is given in the paper and the necessary references. So if you want, of course, you can follow that one. Then the room, as I said, I mean, the buildings are, I mean, the test building, our benchmark is OU44. So we have rooms in this that actually we use as a test case. So we have different type of sensors, and I mean, we have outdoor temperature sensor. So we have, I mean, data on solar radiation, indoor temperature, VAV damper positions, radiator valve position, and occupancy also. But again, I mean, the method does not require all these type of sensors. So you can do it, I mean, with any sensor which is available within your within a room. So we have actually data for 21 days here that actually we use, and half of the data are used for training and then half for testing of the algorithm to see how it works. So the blue line here in this graph is actually the condition indicator for different, as a time series, so for different time instances. And as you can, and the red one is threshold. So whatever you see above this red line is actually indicates actually anomaly. So it's fault or anomaly that we detected. And of course, I mean, the one which is more serious than the rest, as you can see here, is because we left actually one of the windows open just for a test. And that's why you see that it's not acting normal. Yes, so, and of course, we have also explanation of the rest that you could find it also in a paper. Well, so that's what's the result that I wanted to present, but we also would like to improve this result. And I would like to also talk about what we are going to do from now on. So one thing would be that here, as you could see, I mean, it was possible to detect anomaly and fault, but what about diagnosis? So of course, our focus, I mean, in future would be also on diagnosis. I think it's I mean, we know how to do it. There is something called contribution plot that actually tells you that if you have a deviation or violation of a threshold, which sensor is more, I mean, you can order all the sensors with the level of contribution for this deviation that you have. So for example, it can tell you that, okay, the occupancy sensor and CO2 sensor are most responsible for such violation. That it gives you this idea that actually you need to look into basically your VAV of the room, and the ventilation system is responsible, not something else. So yeah, so that's actually of course this type of contribution plot, we have used it for electrical system, we have used it for district heating system, so it's clear for us what to do, and we are going to do that in future. Also, there is something, I mean, we have faults and we have anomalies, which are different. Sometimes, I mean, you have, for example, you see anomalies due to occupant behavior, but sometimes it is actually technical fault. So I think it would be very nice and interesting to be able to distinguish these two. And we believe that actually we can do it, and we would like to invest more time on this distinguishing between faults and anomalies in general. Also, another thing that we are going to focus on is ranking anomalies. So we have different type of violation. Which one is more serious? Because I mean, in time period, you might have actually different violation. Maintenance crew, they have to prioritize. So they need to know where to focus. So if you can actually rank them, that would be very interesting. And ranking is not very straightforward. There are so we are actually looking into some methods that could using a statistical approach like Chernoff bound to basically rank this. And we have tested it on district heating systems. I mean, the fault detection on district heating system, it worked pretty well. So we are going also to invest some time on this one. Then they get a risk, actually the maintenance crew, they get a risk with a probability of how serious, with some number that actually tells how serious this anomaly is, or how, I mean, then they can actually have this prioritization and resource allocation. Then, yes, here I use PCA, but PCA can be improved by, I mean, we can use more than PSA, so more methods than only PCA. And also, instead of squared statistics, so probably we can use other type of statistics to improve the base and foundation of the method also. So that was it, and I'm available for any question that you might have.